in this video, we're going to introduce the angular momentum vector. Then we'll explain how this is related to the torque. So let's look at this, this figure, right, this image. So suppose that we have a particle that has a mass m, and we know the position vector of that particle is this vector right here, is the displacement vector. Now this particle is rotating. So this particle is rotating about the z-axis and with some tangential velocity. So the velocity is in this direction here. So because the velocity is in this direction, it means that the momentum is also in this direction. So remember that the p vector is just equals to the mass times the velocity vector. So the momentum vector is pointing in exactly the same direction as the velocity vector. Now I can define my angular momentum L vector as the cross product of the displacement vector and the momentum vector. So again, if this is my displacement vector here and this is my p vector, then notice that because my displacement vector is on the xy plane and my p vector is also on the xy plane, then when I cross these two vectors here, when I cross r and p, I get a vector that is pointing in the z direction, and this is called the angular momentum vector. So generally, if we said that the sum of the forces acting on a system is given by the derivative of the momentum vector as a function of time. Now, if we calculate the cross product of the displacement vector and the sum of all the force vector, then we know that this is equals to the torque, and so I can write this. So if you just substitute the sum of the force equals to dp by dt, then this becomes the cross product of r and dp by dt. Now, if we take the derivative of the cross product, we use this formula right here. So it's the derivative of r of the displacement vector with respect to time cross the momentum vector plus the displacement vector cross the derivative of the momentum vector with respect to time. Now, we know that dr, so dr by dt gives me the velocity, and because the velocity is pointing in the same direction as the momentum vector, it means that this cross product is going to be equal to 0. Now, if this cross product is equal to 0, then it means that this derivative here is just equals to this quantity right here. And so we can say that the sum of the torque acting on the system, which is equals to this, so the torque, you can see that it just can be written as the derivative of the cross product of the displacement vector and the momentum vector as a function of time. So this is one of the most important equation that we're going to use in this section. So notice that the sum of the torque is just the derivative of this quantity, and this quantity here is just given by L. This is my L vector right here. So you can see that the torque is dL by dt because r cross p is my L vector. All right. So now we're going to define a quantity that is called the angular momentum. So the angular momentum vector is a vector that is given by the cross product of the displacement vector and the linear momentum vector. So this is my definition of my angular momentum. All right. So generally we can write Newton's law. So this is Newton's law for rotational motion. It says that the sum of the torque must be equals to the change in the angular momentum with respect to time. And this is Newton's law for linear motion. So for linear motion, the sum of the forces is equals to the change in the momentum vector as a function of time. For rotational motion, the sum of all the torque is equals to dL by dt. Now, so we can calculate the So in this example right here, we can calculate the magnitude of the L vector. It's just the magnitude of the, so if you calculate the magnitude of this vector, is the magnitude of the momentum vector, which is P, times the magnitude of the displacement vector, which is just the radius, times the sine of the angle between the two vectors, which is given by this. So you want to notice that, for example, when the displacement vector is parallel to the momentum vector, then it means that this angle is going to be 0, and the sine of 0 is equal to 0. So that gives me a magnitude of L that is equal to 0. Now, when the displacement vector is perpendicular to the momentum vector, then it means that the angle between R and P is 90 degrees, and so you get L is just equals to the maximum value, which is equals to M times V times R. So when theta equals to 90 degrees, then sine of theta is equals to 1, and you just get this value for the maximum value of the angular momentum. All right, so let's look at example number 11.3. So this is the angular momentum of a particle in a uniform circular motion. So we said that a particle that is moving in a uniform circular motion means that the angular velocity is constant. The angular velocity is not changing. So when the angular velocity is not changing, then you can see that the tangential velocity is always, so the velocity of the particle is always going to be at 90 degrees with respect to the displacement vector. And so in this example right here, because there is a 90 degrees angle between the displacement vector and the velocity vector, it means that the magnitude of the momentum vector is just mass times V times R. All right. So now we've already said that the sum of the total torque acting on a system is just the derivative of the angular momentum vector with respect to time. So this is an example of a system that is a non-isolated system. So a non-isolated system means that there is torques acting on the system, and the sum of all the torque is just given by the derivative of the L vector with respect to time. All right, so now let's focus on this example right here. So this is example number 11.4. And so we have a system of objects here. So we have two masses. So we have M1 and we have M2. And M1 and M2 are connected in such a way that the cord, so there is a light cord that passes over over this pulley. So notice that this pulley has a radius R, and as M2 is going to move to the left and M1 is going to slide down, then this pulley is going to be rotating in the counterclockwise direction. So there is some rotation that is going on right here. And so what we're going to do is I want to find an expression for the linear acceleration of the two objects using the concepts of angular momentum and torque. So if you want to find the linear acceleration of the system, so we've solved this type of problems before, but the difference here is that now we need to take into account the fact that this pulley is also rotating. So we need to add the acceleration of the pulley into the equations. So I can calculate my total L vector. So I have M1 here. So M1 has a momentum pointing down here. The momentum is just M1 times V. Then if you calculate the cross product of the momentum vector, so my velocity vector is at 90 degrees with respect to my displacement vector. So if this is my center here, my displacement is measured from this center. So there is a 90 degrees between the radius vector and my momentum vector. So it means that the L is just equals to M1 times VR plus M2 VR plus MV times R. So this is the momentum of the pulley. This is the angular momentum of the pulley. So it's just the mass of the pulley times the radius of the pulley times the V. So we can write all of these as that. Now I can write my total torque. So the only torque is provided here. The torque is coming from M1. Is coming from this hanging mass right here. So this torque is produced by the force of gravity. So when I calculate the net torque produced by my M1, then I have force times distance. So M1 times G is my force times the distance that points at 90 degrees here is just R. And so this would be the derivative of all of this quantity right here. So everything here is constant except the velocity. So it means that when you take the derivative of all of this, it's just equals to, you can pull everything out, and then this is just times the derivative of v with respect to t. And since I know that the derivative of v with respect to t is the acceleration, so if I substitute dv by dt equals acceleration, then I can solve to get my acceleration as given by this quantity right here. All right. So now let's look at the angular momentum of a rotating rigid object. So suppose that you have something like a disk, and this disk is rotating about the z-axis with some angular speed. So the angular velocity is given by omega. So what I can do is that I can take this disk and chop it up into like smaller masses, mi. Then I can calculate the angular momentum from each of these masses here. Then I simply sum the contributions from all the masses. So notice that for this mass mi, the displacement vector is at 90 degrees, because if this is moving in a circle, then the displacement vector here is at 90 degrees with the velocity vector. So the velocity vector is always going to point at the tangent to this circle right here. So you can see that because there's a 90 degrees angle between the displacement vector and my velocity vector, then the momentum is just given by mi. So it's the mass times vi times ri. Now we said in the previous lecture that vi is just equals to omega times ri. So if I substitute vi with ri times omega, then my ri is just equals to mi squared times omega. Now if I calculate my total angular momentum by summing all the contributions from all the masses that I have on this system right here, then I get this equation right here. So I can write it as this times omega, and all of this quantity here is just the I value, which is called the moment of inertia. So we notice that in this example here, the angular momentum about the z direction is just given by the moment of inertia times the angular speed. Then if I take the derivative here, so the Lz by dt is I d omega by dt, and I know that the omega by dt is just alpha. So it means that if this is equals to I times alpha, then it means that the Lz by dt must be equals to the torque. So I conclude that the sum of all the torque is just equals to I times alpha, where L is given by this vector right here.